Okay, jumping right in, I'm going to go through question 4 and question 5. 4 is on ruin theory, and 5 is on forwards, futures, and things like that. So, straight in, A, we're given a Poisson process, and we want to write down the definitions for the stationary and independent increments. This can be found in the notes, so we'll just write down that for any kind of time, t1, t2, and the reason that this is less than or equal to is because t1, we could be starting at 0 rather than some other time like that, all the way up to tn. Then the increments n of t2 minus n of t1, and so on, all the way up to n of tn minus n of tn minus 1 are independent random variables. And for kind of some point in the Poisson process, such as S, we have that n of t minus n of s has a Poisson distribution of lambda t minus s, or there's other ways to write it. You can do n of t plus s minus n of s. There's just I think this is seen in other notes. This is the one that we use in ours, but they are exactly the same. So yeah, very straightforward question there. So B, we're given these nice kind of diagrams with plots. Now, just noting the fact that this goes up to 5 and this goes up to 35, so the scale, is different. And from the plot below, we have two paths of Poisson processes with lambda 1 and lambda 2, respectively. It is reasonable to deduce that lambda 1 is greater than lambda 2, justify your answer. So, pretty much straightforward. My answer is just no. So, this is lambda 1, this has lambda 2. And, if we're looking at 5 here, we've got kind of nt of 12. And if we look at 5 here, we've got nt of 2. So comparing this with lambda 2, we've got 1 at that point here. And, knowing that nt is kind of distributed with the Poisson distribution of lambda t, for the same given value of time, nt of lambda 2 is greater than nt of lambda 1. So therefore, it's just not reasonable. And, it's more reasonable to kind of deduce the opposite. Especially even though we're not given any time greater than 5, but, even when we're looking at like 1, up here, this is closer to 0, where here, we already have 2. So I think that's pretty straightforward and quite glaring, especially if you look at, if you look at the different scales. I mean, I know, if you're rushing, you might not, but I think it's quite explanatory. Okay, part C, is kind of a straightforward method-based one. So we have initial surplus of 12 grand, charging their policyholders at 4 grand each month at a constant rate. The company assumes that the claims can be modelled with a Poisson frequency distribution with expected value of 4 claims a month, and whose severity distribution, or by severity distribution, it's essentially just the size of the claims and the value with an expected value of £833 per claim. So essentially, we can just say, we know that our surplus process is UT equals initial, in fact, I'll do it based on formulas, equals U plus CT minus ST. So if we're going to define the corresponding surplus process, we're going to have UT is equal to 12,000 plus 4,000 T for our premium, and then minus the sum up to NT, starting at 0, of XI, or, that's going to be 0 at 0, so we can just, let's say starting at 1. And then all we need to do now is kind of just define NT and X, so where NT is a Poisson process with lambda equals 4, and kind of our X are independent, identically independent random variables. And we want to say such that x1 has or xi, sorry, exp of 1 over 833.3, because it's an exponential distribution, or some distribution, it's the reciprocal. Okay, so we have this, and now we want to calculate the probability of our ultimate ruin, which is essentially the probability that our UT is less than 0, and we can call that this, and we're going to use the adjustment coefficient, and we're going to use Lundberg's theorem. I have no idea how to pronounce it, but we're going to use our kind of premium loading factor rather than our kind of usual inequality of this. So we're going to kind of leave this to the side, and in our notes there's a formula such that if x1 here is exponentially distributed, then we can calculate the ultimate ruin probability with the premium loading factor of 1 over 1 plus theta e of minus alpha theta u over this. So in this way, so we have alpha, or we could say x1 and it is here as shown here, and all we need to do now is really input those values, but we need to find out what our premium loading factor is first. So I'll kind of do this further down here. So we know that C is equal to 1 plus theta lambda, the expected value of x1, and this is also found in the notes, so just make sure you have those with you when you're working this out, or if you remember it, even better. Ideally you do for the exam. And now all we're doing is inputting our values here. And when we use our calculator, this is essentially 0.2 with a good few zeros and then a 4, 8. And then all we need to do now is input it into here. So 1 over 1.2 times e to the minus 0.2 times 1 over 833.33 times 12,000 RU over 1.2, and this is e to the power all of that, and we get a very nice 0.076. So I think that's quite straightforward, as long as you remember this formula and you don't go down the route of this, which I did to start with, and then you also remember our equation for C here with the premium loading factors. So the reason that we can use this is, as I've explained here, because we have that and we know how it's distributed. So it's a fairly straightforward question. Okay, jumping into question 5. This is based on forward contract. I think, to be fair, this is one of the easier questions. So essentially, we've just got 3 definitions that I'm going to quickly go through. So arbitrage is the generation of wealth with no risk. So essentially, your value of your portfolio H at time 0 is equal to 0, and the probability that at t is greater than or equal to 0 is equal to 1, and the probability that is greater than 0 or less than 0, is equal to 0. Pretty straightforward. So then we have, now the law of one price and replicating portfolio is quite, coming together. So we have replicating portfolios if, let's say, VH T is equal to V H dash T for all T in the range of 0 to some capital T, inclusive, and the law of one price not states, but only holds in no arbitrage conditions where the value of these 2 portfolios is the same. So essentially, replicating portfolio is just the same thing, and the law of one price kind of ties their values together because they are the same thing. Essentially, why it's called the law of one price. Okay, B, calculate the forward price of F. So just straight ahead, we know our formula of forward price is equal to ERT S0. So we plug that in, which is £23.50 times e to our 4% interest rate times our length of time till maturity, which is 2 years. Which is £25.46. And there we go. So next, suppose the investor offers you a forward contract on S with a price of £30, assuming that you're also allowed to borrow money and buy coupon bonds and buy or short sell the stock S, construction arbitrage. So essentially, we know that the value of this forward contract for S is 26.46, and we're being offered at a forward price of £30. And because this is higher, essentially what we need to do is we want to go short. There's not really that much guidance, because we're given 5 marks. The mark scheme has no kind of certain bits that it wants in terms of constructing an arbitrage. There's nothing in the notes, so I think it's kind of just essentially what would you do to create arbitrage profit that's riskless, and you might have to just show that in terms of like just basic probability and just writing down our notation from here that this, and therefore we get arbitrage. So yeah, pretty straightforward. Any questions, just let me know. I'm just kind of blitzing through this. So for D, 50 short forward contracts with this one B, suppose that time equals 2, so same time, the value is £27.60. Calculate the value of contracts for the investor at maturity T. Do the investor gain or lose money? So the investor's short, so they're selling at price F, and we know that F is equal to £25.46, and we know that the value at time T is £27.60. So essentially they're selling this value for this price, and because the value of that is lower, because ST is greater than FT, investors making a loss. And to calculate that loss, it's just the difference between the current spot value and the value of the forward contract, and then times by the amount of contracts, which is around £107, not 10.7. And that is the entire paper 2023 to 4. I'll do 2022 to 2024, and if you have any questions, let me know.